Hello, Professor Younger.
Hello, how's it going, sir?
Yeah, two things. First off, I have 14 observations for the moon project.
Mhm.
Second of all, I won't be able to see, I don't think I'll be seeing the moon this week since we're going to get a lot of clouds.
Maybe, maybe not.
When did you say it was due again?
I pushed it back. You can click on the Astro Points things, and it'll tell you the due date on that.
Okay.
Let me know if it doesn't. It's supposed to tell you that.
I just arrived. What?
Yes.
Hello. What were you just talking about?
He's worried about getting enough moon observations in. He said he's not. He only got like 14, and this week's supposed to be cloudy, so he don't think he can get any moon observations in. And I was just telling him I did move the date back, and I think that he can check what that date is on either past emails that I sent, or you can just go to the Astro Points turn-in area, and it should say where that is. If it doesn't, let me know, because I think I changed it to a good 3 or 4 weeks later than it was.
Okay, thank you.
No problem. Anybody else have any questions before we get started? For some reason, I thought I'd already covered chapter 8, but I think maybe I just read it. Anybody know, did I not update my Blackboard, I mean my Canvas to show chapter 8? Because I could have sworn I know I covered it with you. There it is, chapter 8, but no, that's this week. I guess not. Maybe I just went over the PowerPoints in my head. Well, I actually had prepared for either one just because I wasn't sure of that. But if I start lecturing and it's a chapter that we've already covered, just let me know and I'll stop. It's no big deal. Anybody else have any questions before we get started?
I just saw the syllabus. It's due March 24th for the
Yeah, that
moon
was the old date though. On the syllabus, remember I changed it to like 3 weeks later than that. We'll just call it April 15th. How about that? Or whatever the Tuesday is immediately thereafter.
Yes.
I have
That'll
a
do.
question.
Yes, go for it.
Um, for the reflections, do we email those to you, or do we do it through
On Moodle,
Canvas?
you turn it in as a PDF right there in the Astro Points area.
Okay,
Let
so
me
there
double
should be
check.
an area for that.
Yeah, I'm going to look right now. Yeah, there's an area called Astro Points turned in here. And if you scroll down, you'll see chapter 1 reflections, chapter 2 reflections, 3, 4, 5, 6, 13 reflections. It only goes up to chapter 13, but I think that covers all you're doing. Oh, that's right. I skipped from 7, 8, 9. I'm going to make a section just called general, or I'll just call it reflections for other chapters. Just make sure you name the file that you upload with the chapter number, and that you include the chapter number in the like in the title when you turn it in, and you can turn in as many as you want there.
Okay, and do we have to do all of the reflections to get all the points, or
No.
just whichever ones we want?
Yeah, whichever ones you want. I would say definitely focus on chapters 1 through 6, because those are the ones where the science is, and those are the ones you need the best understanding of.
Okay.
So I would definitely focus on that. All right. I see now that I did not, in fact, put the date on the moon project. So let me fix that now while you're here with me in real time. So on in that turn in assign Astro Points here segment, you'll see something called Moon 100-300. And I am going to say file uploads. The only type is PDF. And the due date shall be April. Let's check what that is. I'll say April 15th. That's actually a Thursday, so that's good enough. Okay,
That'll do just fine.
there you go. Any other questions?
Do you know when we can sign up for classes for next semester?
Actually, that's something I should know. I think, can any other student give him a hand with this? Where do y'all go as students to register?
You can do that on the SIS system.
Oh no, I was asking like when we have a good time to actually like sign up for class. Like when is a good time to sign up for classes? That's what.
Oh, I'd say the sooner the better, man.
Okay.
Because what happens if people wait? We end up canceling classes, and then you don't get as large a selection. Not only because other students beat you to the slots, but also because other sections were not allowed. We have like 2 weeks before the actual start of classes, administrators go in and say, you got to cut this class, you got to cut this class, you got to cut this class, because we don't have 7 or 8 or 10 people. So yeah, and I know it's open for, or at least it's open for seeing what classes are available right now, but it's not supposed to be open for enrollment, I think, for another week or two.
Okay, thank you.
Hopefully that addressed all the possible questions. All right, well, we'll go ahead and get started. I'm going to go ahead and share my screen once I can ever find the camera where I was before. Oh, there it is. So anybody else have any questions before we get started on that? All right, looks like we're good to go. And I think I want chapter 8. Again, if this is a chapter, which I feel like I just covered it, maybe I covered it somewhere else, I don't know. But anyways, if I covered it, let me know. You'll be able to tell pretty quickly.
We did chapter 8 like 2 weeks ago.
That's what I thought. Didn't we see that diagram and all that?
Yes.
Yes.
Okay, good. It scared me because I had it on the wrong week in Canvas. So that's good, because I actually did most of my prep this morning for chapter 9, just in case. So let me turn it back to chapter 9. Got more students coming in, so this is good that it helped a little bit. So I'm going to do share screen, and instead I'm going to do chapter 9 share screen. Okay, so this is the chapter that we really should be covering, and it is called Atmospheres of Terrestrial Planets. And you're going to see that using our techniques of comparative planetology, remember we talked about that before? So with comparative planetology, we'll compare one planet to another and not only see how similar they are, but see how different they are, and even look for similarities in their differences. So for instance, if you have something that looks like mountain building on Earth, and it's due to, say, plate tectonics, then you look and you see something that looked like mountains on, say, Pluto, which is obviously not a planet, but just a good thing to argue about. Then you might want to say, okay, well, these things look identical to mountains, yet I know there's no, say, plate tectonics, or I know there's no volcanism or something like that. Well, what could be causing it? And then you come up with this idea of cryogeology, which is basically ice geology. So we don't only look at the similarities and the differences, but we try to find similarities in the differences so that we can further understand not only what other planets are like, but also what planets in general could be like, and understand more about our own planet. So chapter 9 is about atmospheres of terrestrial planets, and you're going to see that actually life plays a critical role in the case of the Earth. So for instance, it says here, let me see if I can move this stupid thing. Why can you breathe on Earth only? That's a pretty good question. We have Mercury, Venus, Earth, and Mars, Jupiter, Saturn, Uranus, Neptune, and we have a dwarf planet named Pluto, another one named Ceres, so on and so forth. But it seems like the only place we're going to be able to breathe is Earth. Why is that? Well, Earth has something that we need, which is oxygen. So we're going to look at this and say, why does Earth have more oxygen, even though they all formed, Mercury, Venus, Earth, and Mars all formed in the same general area? We're going to try to answer questions like that. So that's a really good start off question to think about. And as always, when I don't have reflection questions for the given chapter written, you're welcome to take the learning goals or learning objectives that start each chapter and render them as a question, and then answer that question in a good, robust way and turn that in as a reflection question for that. So if I start making reflection question turn-in areas for chapters other than the ones you've got questions for, that's where you put them. Okay. But each set, like if it's up to 5 questions, it'll be worth 25 points. If you end up writing a lot of long answers on those that are actually meaningful and you going in depth and stuff, then I'll probably give you well over 25. If I go well over 5 questions, I'm going to give you more than 25 points as well. So keep that in mind, especially in light of, we recently took our midterm, and I think everybody realizes that the midterm was a lot harder than our regular online tests. Class averages of online tests are usually in the mid to upper 80s, and then in the midterm, it's often in the upper 50s to lower to mid 60s. So now's the time where people are like, oh, well, maybe I better take this astro point thing seriously. Okay, I got a message from somebody. I was just wanting to make sure I read that chat message. Okay, so how have the terrestrial planets' atmospheres evolved? How did the terrestrial planet atmospheres form? Does the greenhouse effect only apply on Earth? Where are the different layers of the terrestrial? What are the different layers? Excuse me, of the terrestrial planets? I think they meant planets' atmospheres. And how has Earth's atmosphere been changed by life? And how can we use comparative planetology to understand climate change? So this is another thing, and it sort of comes down to the Three Little Bears story. Mars doesn't have enough atmosphere, much less greenhouse effect, so it's way too cold. Venus has way too much atmosphere and way too much greenhouse effect, so it's way too hot, and Earth is just right, but slowly getting not so right. So remember, the new planets formed, and they created what were called primary atmospheres. Those primary atmospheres were basically, hey, there's gas and dust in the nebular cloud in which the planets formed, and the vast majority of that gas and dust was hydrogen and helium, like literally 90-some% in terms of molecule counts, if you will. So initially, all the planets had sort of a little hydrogen helium atmosphere, plus other things, but mainly hydrogen and helium. But hydrogen and helium are both two of the lightest elements that exist. And it turns out that the definition of temperature is that temperature in the absolute scale, the Kelvin scale, is directly proportional to the average kinetic energy of the linear motion of the molecules and atoms making up the thing. So if you want to know what my human temperature is, you'd survey all the atoms and molecules in me and say, hey, what's your mass and what's your average speed? And you take 1/2 times my mass in kilograms times my speed in meters per second squared. So you're going to square that meters per second. And that would give me the average kinetic energy of that particular molecule. Then you go to the next one, and the next one, and the next one, and the next one, and the next one, doing all the molecules and atoms. You add them all up, divide it by basically the total mass, so that you can get the average, or actually the total number, so that you can get the average. And then you multiply that by a couple numbers, or divide it and multiply, and boom, you have the temperature in Kelvin. So you could quickly convert that to, say, 98.6. That's the definition of temperature. So you can see, the higher the kinetic energy is, the higher the temperature is. And kinetic energy can increase in two ways. It can increase by M going up, where if you double mass, you double the kinetic energy, or by V going up, where if you double the mass, you quadruple the kinetic energy. Okay, or excuse me, if you double the velocity, the speed, excuse me, you double or quadruple the kinetic energy. Let me say that again, since I screwed up so much. Kinetic energy is 1/2 mv squared. That means M and kinetic energy, thumbs up, thumbs up. That means kinetic energy and V, thumbs up, thumbs up. But it also means if I double the mass, I double the kinetic energy, because the exponent on M is just 1. However, if I double the velocity, the exponent on velocity is 2, so that's 2 squared, which is 4. So the kinetic energy goes up by a factor of 4. Okay, so higher velocity has a bigger effect than higher mass and kinetic energy. So what that means is, for a given temperature, we're setting T equal to a constant now. That means the M and the V have to be a constant, or at least the M times V squared times 1/2 has to be a constant. With that being the case, the smaller the mass, the higher the velocity. So hydrogen and helium, which are really low mass, will have huge velocities. And you know that any object, no matter what it is, if it reaches the escape velocity for a planet, it can actually escape the planet. Well, it turns out it's a little more complicated than that, because in fact, statistically speaking, if you have a molecule or atom that is traveling at just 1/6 of the escape velocity, and then given hundreds of millions, in fact, billions of years to escape, it will escape. So you really don't even have to reach the escape velocity. But because hydrogen and helium are so light, they're going to have a very high velocity. That high velocity, given the temperature at, say, Mercury, would definitely exceed 1/6 of the escape velocity. At Venus, it would exceed 160 escape velocity. At Earth, it does, and at Mars, it does. So we don't, none of us actually, inner planets, hold on to their primary atmosphere, specifically because the primary atmosphere is hydrogen and helium. Does that make sense to everyone? All right, so just remember kinetic energy, M, thumbs up, thumbs up. Kinetic energy velocity, thumbs up, but squared, okay? And then T is directly proportional to the average kinetic energy. Directly proportional is another word for directly related, and indirectly related, or thumbs up, thumbs down is another word for indirectly related or inversely related. Both of those are sort of synonymous. Now the next thing that happens is a secondary atmosphere. So as the planets go from sort of molten liquidy surfaces, many of the molecules or minerals and rocks that are in that liquid state actually have various gases dissolved in them. And as they solidify, they let some of those gases out, and then volcanoes can erupt and release those gases, and that creates our secondary atmospheres. However, it can also come from accretion. So as we run into, and they run into us, comets and asteroids, those new rocks and minerals and whatever gases are dissolved in them become part of our atmosphere. So that's from accretion, just running into parts, and then comet impacts and asteroid impacts do the same thing as well. So all of that stuff can spell basically a secondary atmosphere made up of various components. All of those components should be elements that we have found in the nebular cloud in the very beginning, which, as we learned before, is basically represented by the spectrum of the sun. So the spectrum of the sun has some 74 elements and compounds in it, and we expect all of those things to be found in the inner solar system or in the solar system nebular cloud total. Okay, so after those secondary atmospheres, of course, we have the same ability to lose those as we do for hydrogen and helium, and then we've got other processes that can steal parts and replace it with other parts and stuff like that. But it turns out after a long period of time, only Venus, Earth, and Mars have significant atmospheres. And to give you some impression of what that's like, well, Earth has an atmospheric pressure around 14.7 pounds per square inch. So sort of like a fairly good sized bowling ball per postage stamp on your body. That's what the pressure of our atmosphere is on us. So every little postage stamp you can fit on your body, imagine a 15-pound bowling ball on that. And that's atmospheric pressure at the surface of the Earth. It's also called 1 atmosphere of pressure, or 760 torr, or 1.01 times 10 to the 5th Pascal. So if you want the scientific units, I've given you all that. But it's, it makes a little bit more sense to talk about a bowling ball every postage stamp. So, and a postage stamp is a little bit smaller than 1 square inch in most cases. So that's why I think that's a good estimate, because 15 pounds is a little bigger than 14.7. So they sort of compensate for one another. So that's what our atmospheric pressure is on Earth. And that's really just due at the surface, basically at sea level, that's due to the column of air directly above us. So every square inch has a square inch column of air that goes from the top of our head, say, all the way to the upper edge of the atmosphere, wherever that's defined. That's atmospheric pressure. If you then go, say, below the surface of the ocean or below the surface of the water, I'm going to say ocean specifically because the ocean has a very specific, nice repeating range. So if you go down 30 feet of salt water, generally speaking, that goes from 14.7 pounds per square inch at sea level to roughly twice that, or 29.4 pounds per square inch at 30 feet. And then it increases by 14.7 again at 60 feet, and then increases by 14.7 again at 90 feet, and at 120, so on and so forth, as long as you're using salt water. So that's kind of interesting, right? So you can get like 4 atmospheres of pressure, or 4 times 14.7. You can get that, say, at 90 square feet, at 90 foot of salt water. Well, to give you some comparison, Venus actually has 100 times the atmospheric pressure of the Earth. So that's 100 atmospheres of Earth. So that's like going down 300 feet below the surface of the ocean. And then on the other end of the spectrum is Mars, which has about 1/100th of the atmospheric pressure of the Earth. So it's a really, really large range. And then Mercury and the moon have essentially nothing even compared to that. But they do have some. I mean, we can actually detect some molecules over the surface of the moon and over the surface of Mercury, but they're really insignificant. Okay. Most people would even consider Mars insignificant, but we don't want to say completely insignificant because we think there is a way we could possibly do something to make it sort of habitable, at least in small chunks. So that's kind of cool. So that started off as our secondary atmosphere, but over time that will change, and atmospheres change by various causes, as we'll see as the chapter progresses. So here's where we start our comparative planetology part. So you can see on the table, it tells you basically planet Earth has a surface pressure of 92 bars. It's almost 100. A bar is another thing for the atmosphere. So one atmosphere is about 1 bar. And you can see Mars is about 1/100th of that, so pretty small. The total atmospheric mass, notice you can see that that's kind of ranging wildly. So they're literally saying, let's add up all the individual masses of all the molecules and atoms found in the atmosphere, and that's what the second column is about. The surface temperature, you can actually calculate it. In fact, your book tells you how to calculate the equilibrium temperature of a planet. It's a pretty straightforward calculation, uses the Stefan Boltzmann law. And it works really well for Mercury and the moon, and to a lesser extent Mars, but it doesn't work so well for Venus at all, and it doesn't work that well for Earth. And that's because the difference is the atmosphere. The atmosphere acts like a blanket. It can hold things in, which is not necessarily just a bad thing. In fact, it's very much a good thing, because the Earth would have a negative equilibrium temperature if it wasn't for the greenhouse effect. So it would be, a little too cold for life to have formed the way we know it. It would have had to form some other way, maybe a less complex way. But you can go too far, which is what the case of Venus is, where we have literally temperatures sufficient to melt lead at the surface of Venus. So that's not a, that's a suboptimal outcome. Okay. The carbon dioxide content is about 96.5% on Venus. So, carbon dioxide is a greenhouse gas. It's not the only one. Water vapor is another one, and we sort of have to have that one. Methane's another one. We sort of have to have that one for life. Certain halogens are other ones, ammonia, stuff like that. They're all, and it's very much polyatomic ions, or polyatomic atoms are basically, in some extent, greenhouse gases. So the carbon dioxide is 96.5% of the atmosphere of Venus. So that's what we mean when we say it's a runaway greenhouse effect, because it really is the exact same thing that we worry most about in terms of a greenhouse gas being run away to beyond a point for recovering. Earth, now at this point, this book was fairly recently published. We recently got a reading of carbon dioxide on the order of 0.07, I want to say. It's been a while since I did the conversion, but the parts per million was 418. And that's sort of one of the highest we've had so far. So it's actually gone up quite a bit even since this book was published. Nitrogen's about 3.5%, but look how huge it is in Earth, 78.1, and 2.7 for Mars. Oxygen is non-existent on Venus. It's about 20%, 21% on Earth, and about 0.13% on Mars. Water is 0.1 to 3% on Earth, 0.002% on Venus, which is surprising that it has any of it since it's so hot. And Mars is 0.02. Argon's 0.007, sulfur dioxide, so on. So you can see all those things, but that's part of the tables that you look at to try to compare what's really the difference between these planets, and then how does that explain the difference in, say, atmospheres, or if you're studying mountains, how does that explain the difference in mountains, so on and so forth. So mostly carbon dioxide comes from the volcanoes, and some nitrogen comes from the breakdown of cometary ammonia. So when you have ammonia that's delivered to us from comets, are also the ammonia that was existent in our solar nebula. The actual sun can hit that and break it up into carbon, and of course, in the case of ammonia, it breaks it down into nitrogen and hydrogen. I was thinking CO2, sorry. And that nitrogen then becomes N2, which is a very, very strong bond. So it's really hard to break up nitrogen. That's how we make one of the major explosives that we use now in warfare, that's non-nuclear because of that great nitrogen bond. But when you do break that down from ammonia, which isn't that strong of a bond, then you get N2, and then that is a very strong bond, and it does start to form. So that's where the ammonia can come from. It could also come from methane, but methane's a little bit harder to break apart than ammonia. It can come from carbon dioxide. Again, difference in ability to break things apart, though, for a given chemical. Make sure you stop me and ask me any questions. I just feel like I'm talking to a stupid computer here, so feel free to stop
Excuse
me.
me, sir.
Go for it.
I just got a flash email on my TCC student account. Says we're doing that tornado statewide drill. I'm like, you can't do it if nobody's in the building.
Yeah, this is where I would tell you, because my phone just went off, I would tell you that, all right, we're going to proceed to the nearest exit. And I, as a teacher, would walk out the room and walk you in the direction of the nearest exit, because I, as a teacher, know the blueprint of the building I'm in and know exactly which room to go, which door to go out of. So I'll just leave it at that, and we'll call that our tornado drill. But thank you for letting me know, because I am supposed to do that, and that was a help for me. So Earth has about 200 times more atmospheric mass than Mars, and Venus has almost 100 times more than Earth. So not only is it thicker and heavier, but it's literally more molecules. So that's really the big difference. The difference with Mars is from the difference in the amount of surface gravity. So Mars, remember, is about half the diameter of the Earth, and its weight's not that big either. So the overall force of gravity is very weak at the surface of Earth. For instance, a previous table gave us the gravitational acceleration at the surface of Mars versus the surface of Earth. We know the acceleration for Earth is 9.8. I want to say it was 2.9 or something like that for Mars, but I'm just pulling that out of my rear end, so I could be just completely misremembering. But I know it's really small, so that's the key point. Venus and Earth are really about 96. Venus is about 96% of the radius of Earth and comparable in mass. So it has a very similar gravity. And those matter when they're talking about being able to hold on to the actual atmosphere, because remember, the formula that calculates gravitational acceleration is very closely related to the formula that calculates the velocity, escape velocity for a given planet. It's got some of the same constants: the G, gravitational constant of the universe, the mass of the planet, the radius of the planet. So here we look at the atmospheric greenhouse effect for the various planets. I would say Mercury has nil, none, zero, nada, right? So, and they're measuring it in terms of how much the temperature has increased, say, or decreased. In this case, it's all positive. So it's how much the temperature has increased as a result of greenhouse effect. So you can look, Mercury actually has, well, I was pointing to this, which is empty, but Mercury actually has this bar right here. And you see that it would normally have a temperature right around, I'd say, 45, 50 Kelvin. But because of the greenhouse effect, it's suggesting that the temperature is considerably higher. I don't know why that's saying that, or am I misunderstood? Oh, I see what it is. Never mind. I misunderstood. That's the range of temperatures. I was thinking of a graph that I had in another book, which was actually showing how much it changed. That was a conceptual physics book I was looking at. Sorry about that. This is the range of temperatures, and this is showing you basically how the greenhouse effect stabilizes the temperature as well. So because Mercury has no atmosphere, when the sun hits it, it gets kind of hot. You know, here it is at what, 700 Kelvin. That's pretty hot. You know, 273 Kelvin is the freezing point of water. 373 Kelvin is the boiling point of water, and we're talking 700 Kelvin. So yeah, that's pretty hot. But if you go to the dark part of Mercury, it'll drop down to, like I said, 45, 50 Kelvin. So that's really, really small. Now you look at Venus. Venus has a very thin little slice here. It basically goes from this extremely high temperature, which is probably 730 Kelvin to 750 Kelvin or something like that. So a really small change. Same thing with the Earth. The Earth has a very small change as well, not quite as small as Venus's, but, or at least it looks a little bit thicker. Mars has a little bit more, and that's because its atmosphere is thinner, so it can't have as much of a greenhouse effect. Jupiter and Saturn, they have a whole lot of weird stuff going on. Once we start studying the Jovian planets, or the gas giants, if you will, you'll see a little bit more details about that. But you can tell, because of the thick atmospheres, their temperatures are pretty stable. Pluto, which doesn't have much of an atmosphere, actually has a little less stability, but it's a little less relevant out there where so many things have condensed to ice. So it still has a range of temperatures. It's just not a very large one. I'd just be hard pressed to say that's due to greenhouse effect. Okay. So really what goes on with the greenhouse effect is according to Stefan Boltzmann law, anything with the temperature radiates. And it radiates in an amount sigma times some emissivity constant, which we haven't talked about, so you don't worry about that. But it's 1 for a black body. It's got some sigma, which is the Stefan Boltzmann constant, and then it's got basically the surface area of the object of temperature T. That is being multiplied by the emissivity and the sigma. And of course, surface area for a sphere is 4 pi r squared, so it's proportional to the square of the radius. So if you double the radius, you increase the radiation emitted by a factor of 4, not 2. If you triple the radius, you increase the flux, if you will, or the radiation emitted, not flux, I should say luminosity, the radiation emitted by a factor of not 3, but 9. And if you quadruple it, you increase it by a factor of 16. And then it's multiplied by temperature to the 4th power. So in that case, if you double the temperature, you increase the luminosity or the radiation emitted by the planet or the star, not by a factor of 2, not by 4, not by 2 to the 3rd, which is 8, but by 2 to the 4th, which is 16. So the temperature has a much bigger effect. So everything that has a temperature above 0 Kelvin is going to emit radiation, but it's also going to absorb radiation from around it and stuff like that. Now, the big thing is that radiation comes out with a profile of wavelengths according to that Planck curve. Remember, the Planck curve had a steep side like this, which was the low wavelength side, and then it peaked, and then it gradually fell back down. That was that Planck curve, or that curve that Planck was trying to explain. That was true about all black bodies, and he had to use E equals N times HF, where N's an integer, to explain it. And when he did, he got the exact equation. Well, that shows us there's a range of wavelengths that radiation comes out in, and Beam's law tells us the peak of that curve occurs for a very specific wavelength. And it turns out that sun coming from our light coming from the sun has a wavelength that is in the visible. It's actually sort of a greenish color or whatever. So that's the majority of the wavelengths of light coming from the sun is in that visible portion of the spectrum. And as you know, our atmosphere is somewhat transparent to the visible portion of the spectrum. Of course, it still has those tails, so it still has some radio waves and X-rays and ultraviolet and all that stuff, but the vast majority of it's right around the visible. So it comes right through our atmosphere, and that then the Earth absorbs it, okay? Well, the Earth absorbs it, and that actually causes it to warm up, but at the same time, the Earth has a temperature of its own, so it emits radiation as well. And the amount of radiation it emits is just like the stuff on Boltzmann law again, only now the temperature is lower. And now the radius is lower, and so on and so forth. Because of that lower temperature and lower radius, we end up getting a smaller curve. And in fact, because the temperature is different, Beam's law tells us that the wavelength will be different. And in fact, the temperature for our Earth creates a wavelength that's in the infrared. So it comes in as mostly visible light. It's almost all the wavelengths, but it comes in as visible light mostly. And then the Earth re-radiates it in the infrared. But that infrared wavelength has a frequency comparable to the oscillation, the natural resonant oscillations of the various molecules or various atoms in a molecule of polyatomic molecules. So for instance, if just like if you kick your feet at just the right rate on a swing set, you will slowly go higher and higher and higher. Well, if you send oscillations at, let's say, 3 atoms on a spring, I'm only showing 2 of them, 3 atoms on a springs connected to each other, if those oscillations are just right, then this will go woo, 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 right? And that's, it's got to make the sounds or it just doesn't work, okay? But if it does match sort of that frequency, then that molecule will actually absorb that light. In other words, the light, just like we did with photons riding by, seeing atoms, and the atom saying, hey, can I use your energy? And if you can, the atom causes the photon to disappear, and the electron jumps up a level. Same thing happens here, but at the molecular level, it says, hey, you photon, do you have the right frequency or wavelength or energy? If you do, I'm going to swallow you up. So the photon disappears, and then the molecule starts going, and those are the greenhouse molecules. They start oscillating. They're in a high energy state. But just like the electrons don't like being in that higher energy state, they're going to fall back down later and emit their radiation in a random direction. The molecules of the greenhouse gases are going to do the same thing. The molecules are going to not like that excited state, and they're going to go, and the photon will actually pop out. Their energy will decrease spontaneously, and the photon will go off in a random direction, almost identical to the original photon, but like I said, this time in a random direction. Now, a lot of those random directions in this upper atmosphere are straight down. In fact, a little bit more than half of them are back down towards the planet, right? So because of that, the greenhouse gases act like this little blanket that sort of keeps some of the radiation in. And again, that's not a bad thing. That sets a new equilibrium temperature for the planet and allows us, for instance, to have liquid water on the surface, which allows for certain types of life to form rather easily, like cyanobacteria and stuff of that sort. Right. And with cyanobacteria, you've got cyanobacteria that absorb carbon dioxide, basically use carbon dioxide and sunlight to get energy. And then their byproduct, or their exhaust, if you will, is oxygen, which allows our atmosphere to fill up with oxygen. So that's what the greenhouse effect is and how it actually affects Earth. But as I tell you, it definitely does help something, because our planet would be too cold without it. But it can go too far, which is the case with Venus, where, like I said, the surface temperature is hot enough. It's about as hot as a pizza oven. Okay. So Earth has much less greenhouse gas in its atmosphere than Venus and Mars due to liquid water. So basically, Earth has much less greenhouse gas in the atmosphere than Venus and Mars due to liquid water. Because of the liquid water, okay, liquid water can actually absorb energy by itself. It is a greenhouse gas, but it's not necessarily, well, it is quite efficient. I'll just leave that for your reading. But Venus was hot early, so no water remained on the surface, and that's because, when you get a higher temperature or a lower pressure, but that's not the case with Venus. Water tends to boil out, and that's the case with Mars. If you put a pot of water on the surface of Mars, the water would actually boil away, not necessarily because of the heat, though the heat could do it, but because of the lack of pressure as well. Because the higher altitude you go, the lower the pressure is. The lower the pressure is, the lower the boiling point becomes. And that's the way we originally tried to find what's the height of the tallest mountain, say, in Africa. People ran up the Nile to look for the source of the Nile, and they just kept boiling water at various locations. Every time they found a huge pond, they would boil water. And if they stayed along the Nile, they knew they were on something that was feeding the Nile. And if they ran into a pond, they boiled water. If they found the boiling point of water was the lowest they had seen, then they know that's the highest point so far. And they say, oh, well, this is a candidate for the source of the Nile. And they keep doing it, so on and so forth. Well, the same thing's happening here. When you get lower pressure, you can have water boil away, or we can get higher temperature, you can have water boil away. So with Venus, the very hot early temperature got rid of a good fraction, if not most of the water. On Earth, the water erosion exposes fresh minerals, which react with carbon dioxide from the atmosphere, removing it and forming limestone. The big thing, well, we'll learn also, as we talked about before, erosion is a big factor with changing our surface, and wind erosion is bad, but water erosion is super, super bad, because the density of water is about 1,000 times the density of air. So that's another reason. But in terms of the Earth has this 2/3 of its surface covered with water, and water has a really high specific heat. So liquid water is not, quote unquote, a greenhouse gas, because it's not a gas, but the liquid water acts as sort of a retardant to slow the change of temperature. For instance, if you look at the latitudes of Great Britain, you'd see they're comparable to southern Canada. Yet Great Britain doesn't have temperatures like Canada, except in the most northern parts. And that's because Great Britain is a small island surrounded by water, so the water temperates the climate and makes it less likely to go super cold or super hot. Same thing with San Francisco. You're surrounded by bodies of water, a lot of water in the Pacific Ocean, which is actually a cold body of water, so it stays a nice temperature year round. That's why so many people like to live in San Francisco. By the way, when you expose these fresh minerals, the things that are absorbed in the atmosphere can actually become absorbed into stone and rock and minerals. And in fact, carbon dioxide would ultimately be able to help form limestone, which is a big part of not only the greenhouse thermostat, but also the big part of how sea creatures and stuff like that are formed, limestone, calcium carbonate, and that sort of stuff. On Earth, life further removes CO2. Remember, as I told you, the cyanobacteria, which we think probably was something along the lines of some molecules like the Urey experiment, the Harold Urey. There's another person that helped him with that, and his name's escaping me right now. But anyways, Urey took a vat of a glass, sterilized glass bulb, if you will, big bulb, and filled it with the initial primary atmosphere stuff that we thought would be on the surface of the Earth. And he sealed it off and he subjected it to light energy, like he expected the early sun to have, the early Earth to have, lightning, volcanic type heat, stuff like that, but not adding any new chemicals. And then after a certain period of time, he found that chemicals were produced that were basically amino acids. So amino acids form the proteins that form basically our cells and our DNA and stuff like that. So that's sort of what we think is sort of the beginnings of our origins of life. That is not origins of life because we haven't got there yet. But we think once you get to the idea of an amino acid that can create a protein, then you can start getting things that are self-replicating molecules. And then self-replicating molecules can recreate themselves and maybe form, for instance, bilipid layers, which would make the cell walls, stuff like that. And next thing you know, you in some ways, and again, we don't know what that is. That's part of the strength of science is one, we tell you when we don't know something, but two, we're not going to conclude it is A until we know fairly certain that it is A. And even then, we're still going to have a little bit of doubt because any subsequent experiment could erase it. But because of that process, we believe over time in water, which is extremely critical to this process, you would actually get cyanobacteria forming, and that would be sort of the first life. And that first life, cyanobacteria, has a photosynthetic process, basically photosynthesis, that can take in carbon dioxide, which is in the water as well as the air, but they're in the water, and can absorb that in sunlight and create its own food. We use ATP, they use something like ATP, but it creates its own food, mainly sucrose. And then the out product or the exhaust of that reaction is oxygen. So the oxygen would then bubble out of the water, and slowly our atmosphere would go from nearly 100% nitrogen to 70% nitrogen, 75%, something like that, and 22% oxygen. So later on will come the greenhouse effect, and that'll help us warm up as well. But in that intervening period, you've got times where there's super amounts of oxygen. At one point, there was so much oxygen that we had creatures that would otherwise not be able to efficiently process oxygen because they need a buttload of oxygen to actually get it to their lungs. Whereas we have a nice big opening hole, 3 of them, for instance, that allows it into an internal cavity. Insects have to absorb their oxygen, or some insects have to absorb their oxygen through their skin in some sense, and other less efficient ways. And when the oxygen was super high, we had those things that were didn't need an efficient oxygen mechanism got really, really big. There's literally fossils of caterpillar type creatures, or maybe it'd be better to say centipede type creatures, that were the size of a school bus. You can imagine how awesome that would be to run into a caterpillar the size of a school bus. But yeah, that's some of the stuff that happens. And we have all that in the fossil record. 2 of the most effective greenhouse gases, of course, are water and CO2. Again, it's water gas. CO2, again, also methane's pretty good. Water is actually really good, but we sort of have a natural limit on our water. Our water has, our atmosphere has a certain amount of it that it can absorb. And if it absorbs more than that, then it becomes, anybody know what happens when too much water is absorbed by the atmosphere?
Does it turn into precipitation?
Exactly. Yeah. When you talk about humidity basically is what fraction of the maximum amount of water is dissolved in the atmospheric air. So if you're at 100% humidity, what that means is a single A single drop of water hitting that cloud that has 100% humidity will cause all of it to fall out. That's the precipitate, which you probably learned about when you did super solutions or learned about super solutions in earth science, where they say, okay, you can take and heat water up and add sugar, and you could add a lot more sugar per volume of volume of water. And when it's warm, it'll dissolve all that sugar, and then you can get some really, really sweet tea. You can then bring the tea back down to a lower temperature, and you can drink it, and you can have super sweet tea, and we can all, grab our insulin needles and have a good old time with diabetes. but still, and I'm not making a joke of diabetes. I'm just making jokes of us and our use of too much sugar. But then, if you come on along later and just add a single crystal of sugar to that super saturated liquid water that's saturated with sugar, then all the sugar will precipitate out. That's why we use the word precipitation for rain, because that is actually the effect that's going on. So yeah, once we reach that 100% humidity, which is based on temperature, of course, but still has a maximum amount, then that water is no longer effective. It's just going to fall out. So we have to have water for life. We have to have water because we've already got the oceans here, and we have a maximum and a minimum of water that can be in the atmosphere anyways, and we're not going to change that. So there's no reason in addressing that for greenhouse warming. Methane, the same thing. Any biological life, any animal life is going to produce methane. So, unless we all cork our bums, we're not gonna get rid of methane. So that's left really with just CO2 as the thing that we're going to have to address most, and halogens, of course, but they're not very large amounts. So here you can look at the Earth's atmosphere, percentage of oxygen levels as a function of time. Remember, the Earth, we think, formed about 4.5, 4.6 billion years ago. So these in billions of years. We think life probably came on the scene right around 3 billion years ago. And that's when the first oxygen released by cyanobacteria. Then all of a sudden you see we had a sort of a percentage of oxygen that was on the order of maybe 6 or 7%. But when the cyanobacteria come on board, then the cyanobacteria start increasing it up to around 10%. Then multicellular organisms can further do the job, and they go up to about 80% of what it is now. And then we have arthropods and so on and so forth. And the oxygen level goes up until the age of the reptiles, which is what we're currently dealing with. So Earth's atmosphere is now mostly nitrogen and a little bit of oxygen. Well, I say a little bit, like 20% or whatever. Other plants' atmospheres, other planet atmospheres don't have O2, and that's mainly because they don't have life. There's not a huge amount of oxygen in the solar nebula, so you wouldn't expect a huge amount of oxygen to appear in the atmospheres of planets. And that's where we are right now. So we have, and not only that, the oxygen that they do have is it's an oxidizer. It's the very definition of an oxidizer. So any metals that are present are going to quickly suck that up. And for instance, that's why Mars is so red. It's literally an iron type surface. I want to say ironic, but that would mean it's something else. A ferric surface, if you will. And when the oxygen mixes with that, it turns it into rust. And of course, rust has a sort of ruddy reddish color. And because of that, we see Mars, even in the sky, as red. So that's it's not that they didn't have any oxygen. It's just most of the oxygen is tied up in minerals. Earth's surface atmospheric pressure is equivalent to about 10-meter layer of salt water. That's what I was telling you earlier. Around 30 feet, 33 feet is really what we use. 33 feet of salt water is equivalent to about 14.7 pounds per square inch of atmospheric pressure. Thanks to O2, Earth has an ozone layer. That's another critical point. Ozone also, by the way, is a protector, but it's also a greenhouse gas. So in some way, it can harm us at this point. But the big thing is the ozone layer is really, really high up, and it's O3 is what it is. Ozone is what happens when oxygen forms O2 with another oxygen, making it O3. And it's actually an irritant. It's something that, like my mother who has COPD, it can actually harm her, or people with asthma or emphysema. It's really bad for their lungs. I think it's somewhat acidic when it gets in their lungs. So it's not a good thing. You've probably smelt it before if you've ever been near a lightning discharge and smelt that sort of burny smell, if you will. That was ozone you're probably smelling. Or if you've been by any of those little experimental or lab devices or demonstration devices that shoot little lightning strikes across, from maybe a little silver or aluminum thing to someone's hand, or grounding rod or something like that, you can smell that smell then. That's ozone, but it comes in small amounts in, so it's not that big a deal. But ozone actually does just like greenhouse gases do. Specifically, it oscillates at just the right frequency where it can absorb certain types of radiation. And in our case, it absorbs UV radiation. And because the absorption of UV radiation, we got a hole in our ozone layer at one time, and it's still there, by the way. And when that hole in the ozone layer presented itself, it actually led to more skin cancers, premature aging, some other health effects that were problematic. And Ronald Reagan stepped in, and I can't remember the name of the accord, but basically in the 80s, he was the first person to ever implement a government law to help the environment on what I wouldn't say hypothesis, but it was a hypothesis on the verge of a theory was telling them was happening to the ecology and biology of our atmosphere, if you will. So he actually stopped using chlorofluorocarbons, CFCs, and CFCs were known to be inert in that they didn't mix with things, which is, you think, a good thing, but it's also a bad thing, because normally when something's non-inert, it would mix with something else and then become sequestered in the ground or in the water, which might be bad, but if it's in the ground, it's probably less bad. But in this case, it was inert, so it didn't bond with anything. So they've been using it in Frigidaire refrigerators for a few decades, when a couple chemists were thinking, well, I wonder what's going on. Where are those CFCs going? Again, CFC is chloro, as in chlorine, fluoro as in fluoride, carbons as in carbon, so chlorofluorocarbons, which basically you probably know the term, hang on, I just lost it, Freon. You probably know the term Freon, that's a CFC. And we now use other things to do the work of CFCs, or Freon, but there's not Freon. So those CFCs were going into the upper atmosphere, and that's what the chemists predicted based on statistical theory. They would go in the upper atmosphere, and they would break down to a certain acid. I think it's chlorine oxide or something like that. I'm not a chemist, so I don't know. But the main thing is that chlorous oxide, or whatever it's called, would take apart an O3 molecule, make it into O2, and then break loose itself and do again. So they actually statistically guessed that it would take on order 1 molecule of ClO, which is what you could get from chlorofluorocarbons, and that might take out 100 molecules of ozone. That was a problem, because ozone is a trace element from the beginning. And sure enough, we ultimately found that expedition up in the north, or excuse me, down in the South Pole, had found an ozone hole, and they kept thinking it was something wrong with their equipment, because it was such a huge hole in such a small period of time. So they literally delayed publishing it for on the order of a decade to confirm that they were doing it right. And then finally they found it, and that was sort of the smoking gun, and got Reagan to act. So that's what ozone does for us. And of course, that's how we can destroy it with chlorofluorocarbons. So that's why the CFC issue became an issue. But in that same case, just like we did with leaded gasoline, just like we did with cigarettes, and like we're doing right now with global warming and carbon dioxide, a bunch of industry people who had vested financial interests made arguments that the science was subjective, it was only on the hypothesis level, and so on and so forth, that it would ruin businesses and it would destroy the economy and stuff like that. But what really happened in all those cases, not only in the leaded gas and in the cigarette industry, which is still ongoing now, but also in the chlorofluorocarbon industry, is a whole new market was created. A rapid search for replacements for CFCs came on board. New technologies were created to make those new products. New industries were made. New employees were hired. Stuff like that. We suspect the same thing will happen, but you do got to make the investment up front, and that's where you could spend a lot of money and get no returns, or you could spend a lot of money and really make way better. So. That's how this chapter sort of interacts with the global warming thing. I'll talk a little bit about that as well later, but right now I wanted to break off and tell you about that in ozone. So that ozone was important to life, specifically because we know that it stopped UV, and UV has the ability to damage cells, which various land forms of life could be a problem. And notice back here on this scale, vertebrates, and then the invasion on land. The invasion on land, if you can see here, was probably about 0.375 billion years, about 375 million years ago. Tiktaalik was one of those. That's a sort of gold trophy for the theory of evolution. A couple scientists made a hypothesis based on the theory of evolution that, hey, I know this species back here is a descendant, or excuse me, is an ancestor of this species up here. I'm going to use the ideas of evolutionary biology to predict an intermediate species, and I'm going to predict its properties, meaning, you know, what's its hips going to be like, what's its brain pan going to be like, what's its feet going to be like, is it going to have fins or feet, or is it going to have some fins and some feet, or is it going to have a tail with a flap on it or something crazy like that? And it made all these bold predictions, predicted where in time you would see it, use the predominant idea of how geology knows the continents came together, and then said, go to this area of Canada and you should find this particular type of fossil. And lo and behold, they found Tiktaalik, and it was exactly as expected. So that's kind of an amazing thing. But again, that shows you how science delivers the goods. You know, we don't make a hypothesis and just let it hang out there. We test that hypothesis, because if we can't test it, it ain't worth crap. That's why so many scientists are bucking against the string theory and quantum loop gravity and stuff like that, because we can't do anything right now, or can't do much right now to test it. We keep looking in it to find ways of testing it at lower energies, but we're just nowhere near the energies that we need to test that. So anyways, back to this. So the atmospheric layers of the Earth are the troposphere. That's where we live, basically. And then you have the tropopaules. And notice each thing occurs with sort of a change in temperature. So in this case, temperature is going down, going down, going down, going down, going down. But in here, it starts to go down a lot less gradually. That's the tropopaules. And then it starts to climb again in the stratosphere. And then, of course, it starts to sink again in the mesosphere. And then it starts to climb again in the thermosphere. So notice that's what dictates the edges of these regions. And actually, tropopaules has some other stuff going on for why we call it the tropopaules. As you can tell, it's not a significant change in temperature, but it does mark the beginning of going up. So, but it's very, very thin. So those are atmospheric layers. You know that, for instance, commercial jets, military jets, spy planes all fly in the stratosphere. Notice the stratosphere is quite a bit below the mesosphere. Record crewed balloon flight was 41 kilometers. That is very well in the stratosphere area as well. We also had, God, anybody remember the guy's name, the person that won the Guinness Book of World Records for the highest jump from with a parachute? He basically took a balloon like this up in the so high in space that it looked like he was totally in outer space. It was dark around him. The Earth looked spherical. You could see the atmosphere, and he then jumps out. And it took like 6 or 7 minutes or something for him to fall. But anyways, he was sponsored by Red Bull, so you can look that up if you'd like. It's kind of cool. As that temperature profile goes, the pressure, of course, goes down, down, down. And notice how low the pressure here is. At the height of Mount Everest is around 0.2 bars, or 0.2 of 14.7 pounds per square inch. If you could even get a helicopter to fly this height, and generally you cannot, it's really difficult to fly at these elevations because the atmosphere is so thin, and drop you off at the top of Mount Everest, you'd probably die in a few hours. That's something to understand. And it's mainly because, there it is, Javier Sotomayor, I think someone said, I suspect that's the guy that did the balloon drop, or excuse me, the parachute drop. Yeah, thank you, Jamin. So anyways, at the height of Mount Everest, the atmosphere is so thin that most people would just die if you drop them off at the top with no acclimatization. But what they do is they slowly climb higher and higher, and they get acclimatized, in theory, to that lower atmospheric pressure, and therefore lower oxygen partial pressure, and they can actually survive it. And the Sherpa people who live at such high altitudes, that they're really good at it, and they're super like mega athletes in some sense. Not necessarily intentionally, but just because that's a way that they can make a living, is by escorting people up. It's so funny. We take people from America up there, and they're like, "Oh, I conquered the world, blah, blah." And they got like 12 Sherpas carrying up all their crap. You know, one Sherpa carrying up like 180 pounds worth of junk. And they're like, "Oh, I'm so tough." But anyways, here goes commercial jets. They fly roughly at the elevation of Mount Everest. That gives you a neat idea, which is 25,025 feet, if I remember correctly. In everyday units, that is. Read Into Thin Air by John Krakauer. Very good book, very entertaining, but very sad. All right, so Earth's atmospheric layers, again, the troposphere is the surface from 10 to 15 kilometers. You don't have to know those things, but you should be expected to know these, at least for this next test that covers this chapter. So you should know troposphere, tropopause, stratosphere, mesosphere, thermosphere. So TTSMT. I was hoping to go, there's squirrels in my pants, but that didn't work out for those of you who know Phineas and Ferb. But there's no squirrels in my pants. It's just a song from Phineas and Ferb. So that's the properties of the troposphere. It's 10 to 15 kilometer altitude. It has temperature and pressure decline with altitude. Most of the water vapor is basically in the troposphere. The tropopause is the temperature stops declining with altitude, so that is a temperature change again. The stratosphere goes up from about 15 kilometers. Notice they're essentially saying the tropopause is essentially 0 kilometers. It's very, very thin. But the stratosphere is 15 to 50 kilometers, and the temperature rises with altitude, as you can see right here. Ozone is present. It absorbs light and heats the stratosphere. So in the stratosphere, the ozone is where we find it. The stratosphere is where we find the ozone, and that's responsible for actually creating the heat that's up there. That's why that temperature is actually climbing. So like when I've talked about the sun having this weird thing, or when I will talk about the sun having this weird thing, that when you get further and further from the surface of the sun, just like when you get further and further from a fire, bonfire, say, it gets cooler and cooler, then all of a sudden it starts going up, and then when you get to the corona, it reaches 2 million Kelvin, which is way higher than the roughly 6,000 Kelvin that it was at the surface. So what they're trying to explain here is, why is this temperature going up? Well, that's because of basically a greenhouse type effect, but in the UV area as opposed to the infrared area, and that's due to ozone. And then the mesosphere after that is the 50 to 90 kilometer range. It has no ozone, so temperature again declines with altitude to the upper mesosphere. And the upper mesosphere is actually the coldest part of our atmosphere. Notice it's a little bit colder than this part. The thermosphere is above 90 kilometers. It's ultraviolet radiation and solar wind can ionize atoms, heating them and creating a plasma that forms the ionosphere. So the ionosphere is really where we get the stuff from the aurora borealis, because that's, a lot of ions in there. And the solar wind is the flow of particles from the sun that obviously can bring those ions. The Earth's magnetic field forms a magnetosphere, which is sort of this envelope that protects us. And because of this, there's this weird law of electricity and magnetism, basically, that tells you how magnetic fields act on charged particles. And here's the rule. It's this weird right-hand rule. But if you have a positive charge going, say, the direction of my index finger, now if it's a negative charge, you have to point it the opposite way. But if you have a positive charge, you point your index finger in the direction of magnetic field. So let's say the magnetic field is sticking into the screen. Now I can turn my finger anyway, and I'm still always pointing along the direction that the positive charge is moving, right? So I can keep doing that over and over and over. But what I want to do is do that until my middle finger, which notice is perpendicular to the index finger, I want to do that until it points in the direction of magnetic field. So let's say the magnetic field points downward. Well, this thumb, which is also perpendicular to the other two, that thumb is the direction the force acts. So if a positive particle is moving through a downward directed magnetic field going towards you, then it's going to take a left turn like that. And it ends up basically making like a positive charge spiral one direction around a magnetic field line. And it'll make a negative charge spiral the other direction around the magnetic field line. And they all converge at the north and south poles, and they create the aurora borealis, because boreal is Latin for north, and the aurora australis, because australis is Latin for south. Orientalis, by the way, which is where we get the phrase Oriental, which I think most people now find offensive, is a word for Eastern, and I think it's Occidental is the Western direction in Latin. So that's how this magnetic field works. So it's a weird little thing, and because of that, it can only apply force in a direction perpendicular to the way it's going, so it never creates work. It doesn't do any work. It's a weird little thing. But now you understand sort of why magnetic field lines act so different, or magnetism acts so different and causes particles to spiral around them and go to, say, the North and South Pole. So you see that the solar wind is coming in. Remember, that's the charged particles created inside the core of the sun, and actually and part of the atmosphere as well, and then shooting off at, hundreds of meters per second coming to us. They hit the beginnings of our magnetosphere at what's called the bow shock, and then they start to alter their coordinates or the directions based on that magnetic field. When they get to the magnetosphere itself, then they get trapped within the magnetic field lines, and those force them, those charged particles, to go either to the North Pole or the South Pole, spiraling in various directions. It blocks much of the solar wind, trapping charged particles from the sun. That's a good thing. Those things that's called particle radiation, and like regular other types of ionizing radiation, it is potentially harmful. So you don't want to get hit by electrons or protons. In fact, electron and proton therapy are cancer treatments, and we only do that to cancer patients specifically because the badness of the cancer treatment is less bad than the cancer itself. So carrying on, there's some pretty pictures of the aurora, probably borealis, since it's looking kind of cold there. And this too, that doesn't look like Australia to me. That looks like it's probably Europe or something. So that's probably a northern or shore aurora borealis as well. I can't tell. I thought this was the U.S. for a second, but it's missing Florida, so I know it's not that. Anyways, what also happens is, yes, sir. Go ahead.
I say it looked like the Antarctica. I think that's Australia up top.
Oh, there it is. Yeah, I see it now. Yeah, okay, gotcha. Yeah, I'm used to looking at quote unquote north pointing Australia, so I was thinking this is yeah, okay, I see it now. Australia was also now thinking, yeah, that is Antarctica. So this is the aurora australis, and this is the aurora borealis. Thanks for catching that. So the other thing that happens is because of these heats and where they hit, they cause changes in little cells of temperature, and those cells of temperature cause a certain circulation. In this case, it's called the Hadley circulation, which transports heat between the equator and the poles. So you get a hot equator because that part is almost always in some sun, right? It's actually, other than the eclipse, during an eclipse, it's always in the sun. Whether it might be 23.5 degrees below the equator or 23.5 degrees above the equator, it's still pointing basically in the equator. So this hottest region is this region. Because of that heat, that heats up the air, that heats up the water, that heats up the air above it. When something heats, it expands. When it expands, it becomes less dense. When it becomes less dense, it floats up. And then because it floats up, it tends to also lift towards the North Pole because heat flows from hot to cold. So always heat flows from hot to cold, but when it gets here, it gets cooler, cooler, cooler. And as it gets cooler, it condenses, or contracts. And that makes it more dense, so it sinks to the surface. And then you get this constant circulation of air going like this. This is the Hadley circulation. And these global winds carry heat from hot to cool regions. So that's sort of like central air for the whole planet. Everybody gets some heat. It's for everybody, right? But obviously, the equatorial regions get more, the tropics, because it's in the tropics of Cancer and Capricorn. Now, because the Earth has this rotation, it has a Coriolis effect, and the Coriolis effect tends to break up these nice, pretty Hadley circles and or cycles, and it can actually cause it to break up into little pieces, and then you get these various winds, and they're called the trade winds and the westerlies and the polar easterlies and stuff like that, and that's where those come from. You've probably heard of the doldrums and stuff like that. So because of all that, those winds can't make that full Hadley circle or Hadley circulation. They get broke up due to varying speeds and the rotation of the Earth and stuff like that. So we end up getting these zonal effects of wind. And the zonal winds are, like I said, the trade winds, which are north and south of the equator, and the westerlies, which are north and south of them, and then the polar easterlies, which are north and south of them. Venus has a hot, dense atmosphere that's completely covered, that's completely cloud covered. Because of that, it has a very high albedo, albedo, not to be confused with the word that sounds like it. Okay, it's albedo, and in fact, it basically reflects, very near 100% of the light that hits it. That's what albedo means. Because of that white surface, most of the heat that hits it is reflected. So it doesn't necessarily take a lot of energy from the sun. Comparatively speaking, because it's just as big as the Earth, but that's mainly because of the albedo. Its surface pressure, like I said, is 92 times that of Earth, and the atmosphere consists mainly of carbon dioxide as a result of the runaway greenhouse effect. Venus has a surface temperature of 740 K. Again, that's hot enough to melt lead. That's a pizza oven temperature. Again, pizza oven, not a regular oven. Thick atmosphere means it's nearly uniform temperatures over the entire planet, night and day. There's a very small range. It rotates on its axis very slowly and in the opposite direction. Remember, we told you about that. And the Coriolis effect is so low that Venus is the only planet to show close to the classic Hadley pattern. So because it doesn't have much of a Coriolis effect is related to how fast the planet rotates. Because of that low speed rotation, the Hadley effect is more or less true. It basically takes everything from the equatorial regions, and all that heat makes a nice complete cycle all the way up to the North Pole, and then down, and then all the way back down to the equator, and so on and so forth. Mars is a cold, thin atmosphere with virtually no oxygen, no ozone is produced. So UV light reaches the surface. That's something we got to deal with if we go there. For instance, right now we got a new rover there, and even some little remote control helicopter thingies flying over. That's pretty freaking awesome. We actually have photographs of the thing taken from those little helicopters, so that's awesome too.
You mean drones?
Yes, go ahead.
You mean drones? Is that what you call?
Yeah, the drones. Thank you.
In 4 minutes.
Thank you, sir. The thin atmosphere means there are extreme temperature variations. You can look just with altitude. Look how the temperature varies hugely with that thin atmosphere. Here's some more pictures of Mars. Temperature at the equator go up to 20 degrees Celsius or 68 Fahrenheit. Temperatures at the pole goes down to negative 150. This is essentially a tornado, right? It's like a dust devil would be probably a more accurate description of it. The consequences of these variations is large winds, which can make big dust storms. We suspect there are winds on the order of 250 miles per hour. For instance, when the polar ice caps melt, they're in the CO2 form, so they go from solid to actual gas. And that, of course, causes a low pressure area to all of a sudden become a high pressure area, and a pressure differential, or a pressure gradient is what they call it. That causes a huge north-south wind of on the order of a couple hundred miles per hour. So pretty cool stuff. Mercury and the moon have ultra thin atmospheres known as exospheres. The exospheres are related to the strength of the solar wind and are probably composed of gas molecules blasted off the surface from the solar wind and micrometeoroids. Combination of temperatures and low escape velocity means any appreciable atmosphere is lost. Now, the big thing about climate, let me give you a quick rundown on this. Yes, we have 3 minutes left. So the seasons we know are caused by the tilt of the Earth's axis, but they have some other factors. The precession of the Earth's axis can actually vary and make us go from 22.1 to 24.5 degrees. When you're at 22.1 degrees, the seasonal effect from winter to summer is less severe, whereas when you go to 24.5, it's more severe. Also, the eccentricity is such that right now, when we're tilted towards the northern hemisphere, tilted towards the sun, so that we're having summer, we're actually farthest away from the sun. But the orbital axis is sort of doing this around the sun. So at some times in the future, on the order of 100,000 years from now, up to 413,000 years, basically that can reverse, where we'll not only be having summer and summertime, we'll also be closest to the sun. And if that happens at the same time that we're tilted to the maximum 24.5, then we'll be even hotter during the hottest time and even colder during the coldest time. And then, of course, the precession changes as well. And because of that, we get another 19,000 to 26,000 year cycle. When all these three effects come in to increase the idea of, or the coldness of our environment, in other words, we're having winter at the farthest point in our orbit. We're having the largest tilt of our orbit, and the precession is such that we're going to have the coldest winter. That can actually create basically ice ages. And this is called the Milankovitch hypothesis, and people thought he was a nut job when he first did it, but we now have some fairly conclusive evidence. There's a few spots of areas where it doesn't show climate consistent with that, but we use these parameters that show the climate as opposed to the temperature. And basically everywhere on Earth, you can see this cycle that basically when all three of those things combine, you'll get periods of ice ages. And we found that is not global circulation model, climate change stuff that we worry about through anthropological sources. That's just the Milankovitch hypothesis, and it's fact, okay? The other one is humans, okay? And humans are somewhere between, I would say, 85 and 97% responsible for the current global climate change. And it's mostly because of the CO2, but you can see other things have a problem as well. Methane is following the same curves. And in fact, 1,860 parts per billion for the for the methane, and 410 parts per billion for the CO2. I told you we're already up like 418 now. We do global circulation models. The time's up. Where basically we divide the atmosphere of the Earth up into shells, and then we divide that up into little quadrants within each shells, and then we set up all these equations that we know are factual with regarding the heat, and we take into account, you know, how much is blacktop, how much is ocean surface, how much is desert, how much is rainforest, all that sort of stuff. And then we make those equations, their programs match the laws of physics, and then we start testing them against past climates, and we make sure that they can predict past climates that we already know, but using temperatures before that and climate data before that. And once it's gone through all those tests, then they can maybe be published, okay? But not until it goes through all those tests. And those tests have been done. I mean, those global climate circulation models have actually been used on Venus and Mars and Earth and Europa and stuff like that. And we find they're right, okay? So that's why we're confident in them. And we also find that the CO2 currently in existence in our atmosphere is really depleted of carbon 14. And that's indicative of the CO2 of modern day Earth coming from the burning of fossil fuels, because fossil fuels should have no carbon 14 in them. I'll leave it at that. I think that's sufficient. Next time we will meet, and I'll probably take some more questions on that. I might talk some more about global warming. You guys are free to go, of course, because the time's up, but I appreciate you coming. I'm going to put up a turn-in area for the various reflections too, so you'll see that in the Astro points.
Have a very nice day, sir.
You too. I hope y'all enjoyed that. Sorry you were less excited. Jamie Lynn, you have a question? I got your email. How about you, Heath? You got a question, or are you just logged out and not know it?
Sorry, I was going to the bathroom.
That's good as you muted it.
Have a nice day, sir.
You too, see you, Heath. I guess Jamie's not here. Are you, Jamie? All right, we'll call it a day then. Y'all have a good one, folks.